Okay, so today we're going to continue talking about economic modeling, how to solve economic models, and we're going to give you this, what I consider to be an important example, which is the national income model. It's from Introduction to Macroeconomics. It's the fundamental accounting equation for national income in macroeconomics. And look what I have on the screen. You can see there's this equation, y equals c plus I plus g. Sometimes you'll actually see a plus nx there. Oh no, my internet connection is unstable. Can you guys hear me?
Yeah, it just kind of lagged for 1 second.
I wonder if my kids are using too much internet bandwidth. They have virtual school right now, but we'll see what happens. I think I should be okay. Might have to bump up this internet speed. Okay, but my point is the national income model all sort of centers around this equation, y equals c plus I plus g. Sometimes there's extra parts of it, but that's what it is. Let's take a look now at this assumption that I and g are exogenous. Hopefully you guys know what that means. Exogenous means it's not included inside the model, it's outside the model. And here's one sort of helpful notation. You see how this I has a 0 in the subscript, I 0 and G 0 in the subscript? Those aren't O's, those are zeros. This is what you may commonly see for a variable to indicate that you're talking about the number, that variable fixed at a particular time, time 0. And you treat it as exogenous. This isn't always true, but a very common notation is I0 indicates that I is an exogenous variable. G0 indicates G is an exogenous variable. And then I asked you this question, can this model be solved? Yesterday, or last Thursday, and somebody answered correctly, no, because there's only one equation. And how many endogenous variables are there? Y and C. That's two endogenous variables, but only one equation. Does everyone see why that means you can't solve it? Anytime there's more endogenous variables than there are equations, that means you can't solve it. Agreed? Does it make sense? I guess, does anyone have any questions about that? Okay, let's continue. So you can't solve that model because there's only one equation. But what if you add another equation? Sometimes this one's called an equilibrium condition. And it's just that c, the variable c, is equal to 10 plus 1/3 y. He's waiting to get in. I will admit that person. Okay, so now I'm only showing you one equation on this slide, but you think of that as being added to the previous equation. Now we have two equations, two unknowns, and you can solve by substituting and eliminating any variable you want, but let's do C. C is the best one to eliminate. And but it's unfortunate that I don't have both of these on the same graph, but you take this y equals C plus I plus G, and where it has a C there, I'm going to replace it with 10 plus 1/3 y, because that's the second equation. And what you'll get is, instead of y equals C, that C has been replaced by 10 plus 1/3 y plus I0 plus G0. By the way, I hope you remember that these variables I and G have a 0 in their subscript in order to indicate that they are exogenous to the model, okay? So y equals what used to be C plus I, which has a 0, plus G, which has a 0. Do you want me to show you how I get from here to here? Let's do that. This is the kind of thing that'd be so easy to do on a whiteboard, but I got to switch to my phone. I will spotlight this video. Okay, what do we have here? Y equals C plus I plus I0 plus, oops, that's not a G. I said the word 0, right, as I was doing that. Okay, that's the first equation of our model. The second one, if I recall, is C plus, what was it, 10 plus 1/3 Y. I'm going to solve this by substitution, and that is Y equals 10 plus 1/3 Y plus I0 plus G0. I'm going to see here that if I subtract 1/3 Y from both sides, it will become 2/3 Y over here equals 10 plus I0 plus G0. Now multiply everything by 3/2. You get Y equals 15 plus 3/2. I'm going to put a star here. Why do I put that star there? It's because we solved it. Oops, Kevin. Often a latecomer, but I got to admit him anyway. Welcome, Kevin. We just solved the national income model example that I have on my lecture notes.
Hey, Professor, I actually just got discharged from the hospital.
Oh, sorry.
Yeah, I had an allergic reaction to medication that I got prescribed last Friday afternoon. I guess I fell unconscious. I was like outside my house, and somebody found me. They called 911, brought me to the hospital. So I've been there over the weekend, and
Damn.
they put me on. I guess my primary care doctor didn't realize I have one kidney, and because of that, I had this adverse reaction. They put me on some like liver meds and.
Wait a second. Maybe I shouldn't be recording this, Kevin.
Oh, okay.
The whole class can hear you.
It's not worry about it.
I just don't want you to reveal anything sensitive.
I don't mind. I'm not worried about it because it's not a big deal. But like, yeah, I'm actually on my way back to my place. I just need to I haven't showered in a few days. I need to clean myself up.
Okay.
But,
well, you can talk to me later about this. I'm sorry about the problems.
Oh, no, it's okay.
Okay.
No problem, man. Yeah, but I can log into the tail end of class really soon.
I'm gonna record this, and
Okay.
you can watch it then too.
Okay, I appreciate that. Thank you.
Okay. Let me go back to the fact that this is the answer for Y. I give a Y star to it because it's solved in terms of only the exogenous variables, right? Don't be alarmed that there are these I and G here. Because what about C? We should go back and solve for C too, shouldn't we? Let's use this equation right here, this one. Plug in what we know for Y as Y star into that. And what do we get? C equals 10 plus 1/3 Y. I'm going to plug in what I got for Y there. And that is 15 plus 3/2 I0. I'm going to actually multiply that out, 3/2.
I have a quick question. I was a little late to connection problems, but where's the 1/3 from again?
It comes from here.
This is from the homework, or just?
No, this is from my example on my slides.
Okay, cool.
I'm going to show this to you again.
No, I think I took a picture of it, so I wasn't sure.
Look right here. Add the equilibrium condition C equals 10 plus 1/3 Y.
Okay, cool.
So now I'm asking you to solve this national income model with two equations. The first one is this, Y equals C plus Y plus G. The second one is this, C equals 10 plus 1/3 Y. So I just wrote those two equations down. I wrote those two equations down here on my piece of paper, and I solved this equations, and I got Y star.
All right, yeah.
That's the answer for Y star. Now to find the answer for C star, we got to do a little bit more. You have a 10 plus 1/3 of 15. 1/3 of 15 is 5, so 10 plus 5 is 15. Now we have plus, is that right? Go. I don't see anything wrong. 15, now 1/3 times 3/2 is 1/2. I'm going to say 1/2 I0 plus G0. I think I'm okay to put a star by that too. Does everybody see how I got to Y star and C star? And that's in fact the quote unquote answer to this problem. I'd really like you to ask a question. If for any reason you're like, I actually don't see how you got that, or why is that the answer? That sort of thing.
Yeah, I'm kind of confused as to how you went from C equals 10 plus 1/3 and all of that to the C equals 15 plus 1/2 I plus C.
I just multiplied this out. 1/3 times 15 is 5, right?
Oh, I see. I see what
And then I added 10 plus 5 and got 15.
Okay, that makes sense.
Yeah.
Thank you.
No problem. That's a little thing. I'm also asking if you have any bigger picture questions, like why is it that this is what you're looking for, Y star and C star? The answer to that is this is a model that has two endogenous variables. It means those are the variables we care about. You wrote the model because you care about those variables. You want to solve for them in terms of the exogenous variables, and that's what we've done. Because remember, I and G are exogenous. How did we do it? We just used some algebra and some substitution. It could be that later on in this class you use some techniques that are beyond this, but still fundamentally you're doing the same thing. You're looking to solve for whatever the variables that you care about in terms of anything else, something that's fixed, like a parameter or exogenous variable or a constant. Okay?
Sorry, I have one more question.
No problem.
This is kind of more for the homework, but
Yeah.
for example, I and G both have constants in front of it, and because they're exogenous, are you allowed to like add them together and just make it I and G without a plus sign in the middle, or how does that work for example in a quadratic formula?
I wouldn't put I and G together. That usually means they're multiplied.
Oh, okay, I see.
You know, and treat them just like a number. So, okay, so yeah, you're going to need to use the quadratic formula in the homework. I think I have the homework here if you want to see it. What the heck? I feel like helping you guys. I want you all to do well on your homeworks. So how can I help you do that? I want to share that. Share this. Okay, here's the homework. I think I can zoom in. Maybe even more. Okay, so here's the problem. It's different now, don't you see? And because there's a y in the denominator, it's not going to be linear. Okay, you're going to have, once you plug this in here for c, what you're going to have to do is essentially multiply everything by y plus 10. Right? Once you do that, you'll have a y plus 10 times a y over here. That'll be y squared. You will actually have a quadratic formula for y. You'll have eliminated c, because by plugging this in, you'll have eliminated c. That's good. But what you'll have is a y squared and the constant term for y and a linear term for y. I'm sorry, a constant term and a linear term and a quadratic term. Then you have to use the quadratic formula, which if you don't remember it, it's on my slides. And if you want me to say it right now, I will. It's negative b plus or minus the square root of b squared minus 4ac, the whole thing over 2a. That is the quadratic formula. So you can use that to solve for y. Oh, I have that in my hint. It'll give you two possible answers, and it's okay to leave your answer with the plus or minus sign to indicate that solution is plus or minus something. I want to see what you guys are. I want to like see your faces now. Let me see. Okay. Are you guys okay with this? I want you to do well on the homework, and it's due. I think it'll be due Thursday. So, you understand what I'm asking you to do? I see a lot of shaking heads. Yes. Jalen says no. Okay, that's okay. That's cool. Um, did you understand when I did it on the piece of paper here?
Yeah, I understood up until I understood how you got to the Y star. The C star, you did explain it. I'm pretty sure it's more of like a fundamental lack of understanding. I did follow you up until the Y moment. I have seen this function before, but yeah, I was just a bit confused more so how you got from C to C star.
Wait, you mean here, going from here to
Right
there?
there. Yeah.
All I did was take 1/3. Maybe I should have written out that extra step. Let me do the extra step that I skipped.
Okay.
Here's the
I
10.
really appreciate
That's
it.
that 10
Okay.
plus 1/3 times 15.
That should be 5.
Yes. Plus 1/3 times 3/2 times I 0.
Okay. All right. So you distributed it. Okay.
Yeah, I distributed it.
Okay.
1/3 times 3/2 times I 0. That whole thing becomes.
Okay. All right. Yeah. I think I understand much better now. I
Good.
was confused by that one.
No problem.
Thank you very much.
Cancel the spotlight video. Wait, so wow, I should be able to see everyone. Okay, so this means on the homework problem, it's going to be a quadratic equation. I did that on purpose. I want you to have some practice with quadratic formulas. So, but the process is still the same. You're solving for y star first, and then you're going to solve for c star, and that will be your answer. What I've given you after this, as a bonus, is I asked you to come up with the comparative static for this. And I haven't taught you yet what a comparative static is. So I think I should do that now, okay? Unless anyone has any other questions, I think I should go on to that. Where do I have that? Here we go. It's my very next slide, of course. This was intentional. More. Nope, sorry. I keep sharing and unsharing. It's very complicated. The world of virtual learning. Okay, here's comparative statics. You should be able to see that on the screen. What is it? Well, it's when you see how the changing of an exogenous variable or parameter affects the solution to your model. You may be thinking, what the heck? You just told me that exogenous variables you pretend like they're fixed, like they never change. That's what you're doing, right? You're saying it never changes, so it's an exogenous variable. Well, comparative statics says, okay, we changed our mind, and actually this thing which is exogenous, we're going to allow that to change, and we're going to see how that affects the solution to your model. For example, what if this variable G0 increases by 1 unit? What happens to the Y in the previous national income model? Before you look at this answer, let's go look at this answer, this number right here. Y equals 15 plus 3/2 I0 plus G0. Can somebody just tell me what happens if G0 goes up by 1? What happens to Y?
Does it go up by 3/2 of 1?
3/2 of 1 or just 3/2? But yeah, that's right.
Yeah.
William gave this answer. He's correct. You guys see why what William said makes sense? Even if I don't know what G0 is, if I know that G0 gets larger by 1, I know that whatever happens to Y is 3/2 times that 1. So yes, Y is going to get bigger by 3/2. You can answer that question without even knowing what G0 is. Don't you agree? Good. So that is what we call a comparative static. The word static means it's not changing. You know, a static model is one where we just look at it at like a snapshot. Here's how it is right now. That's a static model. Whereas a comparative static says, well, we're going to look at what it would be if it were static in this case, and what if it were static in this other case, and we're going to compare them. And so this thing which is not changing, G0, actually is changing in the comparative static. So the answer to that question is 3/2. Okay? It's just called a comparative static. Shrink this. The answer, because we found the solution of y equals 3 halves, 15 plus 3 halves I0 plus G0, we can see that the increase of G0 causes y to increase 1.5 units because that is the slope of the line. Note this is also the derivative of y with respect to G0. And the best way to write this answer is to say dy dg0 equals 1.5. Okay, this is my introduction into calculus for this class. This is the first case where we really would like to use calculus to have a better description of a comparative static. Rather than just like this general thing, what happens when you change an exogenous variable? Let's get more specific. And hopefully you're okay with this notation with the d something over d something. It doesn't mean divided by. It doesn't mean dy divided by dg0. This is a notation. And the way you read this is as follows. The derivative of y with respect to g0. So whenever you see something d something over d something, you say it's the derivative of the top thing with respect to the bottom thing. Like this down here, look at my bottom bullet point. It says question, what is dc over dg0? This is notation that I'm using and I want you guys to know, be familiar with this notation. What does this mean? It means the derivative of c with respect to g0. The question now is, are you comfortable with the concept of the derivative? And I will need to teach you something about that. Or as I was saying earlier, it's going to be kind of a review. I hope that you've seen it before. You're supposed to have seen some calculus before, I believe. And therefore, if you've never had it before, there might be a little bit more work you have to do to get caught up in this part of the class. But I'm still here to help you. I'm still here to answer questions and make it easier for you. Okay, that's the end of that. So, by the way, can somebody answer what is dc dg0?
Would it be 1/2?
It is. Jordan, how'd you know that?
Because the slope on G is 1/2.
The slope on G. You mean in the C function, which we saw?
Yeah, in the C function, the slope on G is 1/2.
Yes. Or. Oh, okay, Jalen. I got your note. Okay. So. I totally agree with Jordan, but one sort of clarification for how you would say it, you would say maybe even C star. I didn't put stars here, but it's sort of an understanding when you're doing comparative statics that the endogenous variables like C or Y that should be treated as if they've been solved already in the model. So like maybe it's more accurate even to have a star there. I left off the star for simplicity, but you treat the C and Y as already having been solved, and then G0 as the thing that's changing. Just as a word of caution, because if you had looked at this first equation, y equals C plus I plus G, you might say, what's dy dg? It's 1, isn't it? It looks like 1. It looks like the slope of this is 1. Because the coefficient of this G is 1. That would be the wrong answer, okay? It's weird because the reason you can't just take this equation and say dy dg is because there's an there's an endogenous variable right there, this C. So if you tried to take the derivative of this, and try to use that for your comparative static, you would just be wrong. What you need to do solve the model and get this formula for y. Oh, sorry, it's right here. This formula for y, 15 plus 3 halves I0 plus I0, and then take the derivative of that and get 3 halves for this question, or 1.5 for this question, and 1/2 or 0.5 for this question. Okay, I think that's all I have to say about comparative statics. I think I might, for time's sake, I'm going to skip talking about logarithms and exponential functions, even though they are necessary. For right now, I'm going to go straight to derivatives. there may be some issues because we want to take the derivatives of log functions and exponential functions, but I'll explain them to you as needed in the context of differentiation for the interest of time. So let me pull up what lecture notes I have about differentiation, which are also posted on Blackboard. Where are they? It's coming up. Okay. And then I need to share that with you. It says economic modeling. It's not right. Differentiation is what I want. I don't know why it won't let me share the differentiation PowerPoint. It's not even an option. Okay, maybe. There it is. It's on my computer, but it wasn't available for Zoom yet. Okay, here is a review. It's currently 1:02. The class goes till 1:45. So this is at most a 45-minute review of differentiation, a class that you could take 5 weeks or 10 weeks talking just about differentiation in some classes. I don't know. In high school you probably did. You took calculus in high school, but in college, anyway, it's a big topic. I'm going to have to condense it for the concept for the purposes of time. Enable editing. Oh, why did I do that? I just want to show you the slideshow. So here's the concept of the derivative. It's very important in all of math and especially math economics. It's very, very, very important. But how should you think of the derivative? Well, here's two main ways to think of what a derivative is. It's the rate of change over time. Basically, how fast something is changing over time. And you might say, what if there's no time? Okay, well, maybe it's how fast something is changing over something else that's moving forward the way that time moves forward. That's another way to think of it. Another thing you can think of is just the slope of the tangent line. What is a tangent line? You guys know what a tangent line is? It's a line of a curve. It's kind of important actually. So let me share real quick a whiteboard. It's not going to be great, but hey, here we go. I want to just make sure everybody knows what a tangent line is. It's going to be important in the future. Okay, here I'm going to draw a curve. Let's do it in green. Here's a function. We'll call that function f of x. And what I'm telling you right now is the derivative. Let's also call this y. The y-axis and this the x-axis. Remember how I said dy. This is hard to write. I'm writing with my mouse right now. I'll try to get something better later. But the derivative of y with respect to x, you can think of that as the tangent of this function. In other words, the slope of this function is dy dx. So at this, let me get some things here. I'll do this in what red. So here's a tangent line. Why is it tangent? Because it touches only this point right. I just want to make a dot right here. Okay. So right there at that dot, you can imagine this red line is tangent to this green function. And we think of that as the slope of the function at that point. This concept dy dx is a way to give that a numerical value for the slope of this function. Another way to think of it is the rise over run. If you don't know what slope is, I think you do know what slope is, but just as a reminder, like the rise over run, how fast it's going up divided by how fast it's going over, that's the rise over run. Okay, so that's what dy dx is. You know why it's going to be so important for economics? Is because it will be important for optimization and like finding where this green function is maximized. That's going to happen where the derivative is 0, right? Because at least, well, of course it gets bigger over here, but of course if I'm just looking at a certain range, I just want to draw like here. Here's a range. And if I wanted to say, what x could I choose in this range that would maximize the function f? That's not drawn very well, but I think there's a point right here. And we might even call that point something special, like x star, like the optimal x, the best x we can find on this range. What's so special about x star? Well, it's the maximum point of this function f, and it occurs here. Let me draw just a line. I really wanted this to be flat. Okay, that's where dy dx is 0, right? Here at the red dot, dy dx is positive, and that sort of tells us it's not the maximum point because dy dx is positive because it's an upward slope. But here at x star, dy dx is 0. That means actually it probably is the maximum on this, at least on this range, it's the maximum. And then if you found a different point over here where dy dx is negative, it would be downward sloping. That wouldn't be the maximum either. So this is a big reason we want to be able to find derivatives, is so that we can take a function, take the derivative of it, and set the derivative equal to 0, and then we look for these points here, these x stars. Sometimes they're called critical points. So that's what we're doing now. We're looking for, we're learning the rules of differentiation so that we can take the derivative of any function. Give me any function, I'll take the derivative of it. And then I can look and see when is that derivative equal to 0, and then at least that gives me a possible optimal point. Why do I say possible? Because here's another point where the derivative is 0, isn't it? Oops, that's supposed to be a straight line. But here's a point where the derivative is 0. Here's another point where the derivative is 0. One is a maximum and the other is a minimum. Right? So a lot of this class is going to be about figuring out what does it mean to actually be a maximum or actually be a minimum, not just for functions of one variables, but for functions of multiple variables. Right now, I'm showing you a two-dimensional graph. There's the x-axis, there's the y-axis. But in the future, I'm going to be talking to you about functions that you can't draw because there's just too many dimensions. But you can still use these techniques that involve the derivative to find out where the functions are maximized or minimized. That's the point. That's what I want you to sort of have in mind when we proceed with what we're going to do today, which is learn the rules or review the rules of differentiation. Okay. I'm doing a lot of talking now. Does anybody have any questions? I'm going to sort of skip this definition. This is actually the actual definition of derivative is written as in terms of a limit. This is like saying, I want to get this sort of represents the slope of a function taken over some interval of x, some delta x, and then you want to take you want to let that interval delta x get as small as possible, all the way down to 0. Then it's no longer an interval of x, it's an actual point on the function, and it refers to the slope. And here's some other ways to call it or write it, which you might see in this class. And I want you to be okay with it written any way. So if you see f prime of x, that means the derivative of f with respect to x, same thing. If you say dy over dx, that means the derivative of y with respect to x. But it's the same thing as f prime of x. You might even see it this way, d of dx, d over dx of f of x. This means, like, once again, the derivative with respect to x of f of x. All these three bullet points are 3 ways of writing the same thing. Okay? I don't know if I want to do this tedious example, but if you wanted to know what's the derivative of this function x squared, you could actually use the definition of the limit and simplify it all the way down till you get to this 2x. So you actually don't need to use the rules of differentiation if every single time you find a function, you do this, you use the definition, but I strongly, strongly, strongly recommend you do not do this. This would be a waste of your time to say, okay, I want to plug in x squared here, and I'm going to get all this and simplify. Okay, now I have an answer. The much, much, much faster way is to take a function like x squared and to know in your head what the rules of differentiation are and say, oh, I know what the derivative of x squared, it's simply 2x. And probably most of you already knew that, right? Why is it that the derivative of x squared is 2x? What's the rule that goes from x squared to 2x? Anybody want to share with me, just to make me feel like you guys already do know some of this, which I'm sure you do. How do you get from x squared to 2x? What's the rule?
You take the
no?
exponent off of the variable and then put it in front of the variable.
Okay, and one more thing. So if it was x to the fourth, would it become 4x?
The third, I believe. I'm sorry for cutting you off.
You're right, Jalen. Jalen got it. I think you meant that, William. You just
Yeah,
didn't say
so
it.
you move it and then you subtract the exponent by 1. So if it was to the second, then you would
Perfect.
take it away. But if it was to the third, then
Perfect.
the exponent would go to the
Yeah,
coefficient.
you're the guy who said you didn't know how to take derivatives, and actually you are perfectly correct on this. That's called the power rule.
Yeah, I'm having like major
Yeah.
like
Yeah.
deja vu like flashbacks.
Cool. No, thank you. Thank you for answering. So that's the rule. It's called the power rule, and I've written it right here. The third one here is called the power rule. So when you're, don't get like, this looks weird with all these. Let me just go through these one by one. Anytime you want to take the derivative of a function that's multiplied by some constant, so c is a constant, f is a function, what's the rule? We can simply just take that constant outside of the derivative, right? So this c, which was inside the derivative, it can come outside. Anytime you have a sum or a difference between two functions like f and g, I can take the derivative of those two functions separately and add them if there's a plus, or subtract them if it's a minus. Those are very useful. Use those all the time. Power rule, that's the one Jalen was describing, and William got it started outright that if you have x raised to some power n, and you want to take the derivative of it, you just take that n and move it outside as a coefficient to the x, and then you reduce the exponent by 1. So n becomes n minus 1. So x squared becomes 2x. X cubed becomes 3x squared. X to the fourth becomes 4x cubed. This is a very, very useful and commonly used rule called the power rule. Okay, I didn't talk to you about exponential functions or logarithms, but I'm sorry, I have to assume you've seen these before, and you're not just like, what the heck? What's a logarithm? What's an exponential function? I can explain them quickly to you now, but I think you'll be okay. If you want to take the derivative of some function, which is now x isn't the base of the exponent, it's the power of the exponent. So this isn't like x to the n, this is something else, a to the x. How do you take the derivative of that? Well, a to the x, you pretty much just leave it as a to the x. You don't change it at all. All you do is multiply it by this constant, the natural log of a. Okay? ln refers to a natural logarithm. And just in case you don't know what a logarithm is, it's the inverse function of an exponential function. So it's like saying, to what power would I have to raise? So let me look at it. This is the easiest logarithm to look at. So we have log base a of x. That's how you would read this, log base a of x. What does that mean? What does log base a of x mean? It means, what power would I have to raise a to in order to equal x? That's what a logarithm means. So for example, if a is 2 and x is 16, then log base 2 of 16 is equal to 4, because 2 to the fourth power is 16. That's just what a logarithm is. And you might say that, you know, what the heck, why, if it takes you 10 words just to define the function, why would you care about such a weird function? It actually comes up a lot in economics, like even more than exponential functions. Logarithms are used like daily by economists. It's just something that appears a lot. Part of the reason is we care about growth, and growth is tied to exponential functions and logarithms. Another thing is we care about functions whose evolution is related to some state variable. In other words, there's like a feedback mechanism where you know, the rate of change of x is a function of x itself. Anytime you have a function that looks like that, it's going to be exponential and logarithmic. So it comes up a lot in economics. So here's my point. I want you to know these rules of differentiation. All of these here. There's going to be more in the next slide, but do you guys have any questions about these 5 rules? We're going to need to do some examples, of course. Examples are the best way to teach something like this. And remember, it's like a review. By the way, nobody asked any questions, but I need to talk about these special cases. The special case in each bullet point is when this constant a happens to be equal to e, where e is the exponential number, Euler's constant, which is 2.718 approximately. Whenever the base of an exponent, the base of an exponential function is e, it's this very special case where the derivative is itself. Besides 0, this is the only function whose derivative is itself, e to the x. Okay. And similarly with logarithms, when the base of the logarithm isn't just any old constant a, but the constant e, which is 2.7, we call that the natural logarithm. And it's also very special because the derivative of the natural logarithm is 1 over x. So that's helpful to use. They both become very easy to differentiate when you use e. Okay. Any questions about this? I want to get to some examples. Also, I ask you to take derivatives on your homework. So I remember the goal is for that to be due by the beginning of class on Thursday. So I want you to be able to do all that stuff. Some of you maybe already have. Okay, here's more rules of differentiation that once again look harder, but let me explain them to you before you get to. Oh, did I also? Oh no, I didn't use the chain rule. Where's the chain? Oh, there it is. Yeah, the chain rule. Okay, let's do these one by one. The first bullet point is the product rule. Remember before when I said if you want to take the derivative of f plus g, you could just do it separately. If you had f plus g, you're allowed to just take the derivative of f separately, and then take the derivative of g separately, and then add them together. And I mean that whenever f and g are functions, you can do that separately if they're being added. But if they're being multiplied, you cannot do that. You'll get the wrong answer if you don't use the product rule. So it's worth me going over this product rule right now. And that is, if you take the derivative of f times g, and that's like 2 functions being multiplied together, I have to solve it in this separate way, which is to say the answer is f. Just leave f the same, whatever f you started with, leave it the same, and multiply it times the derivative of g. That's the first term. Plus, now I have g, and I'm going to leave g the same. Whatever was g, I'm going to just leave it the same. But I'm going to take the derivative of f and multiply it together. Another way you might see this is f g prime plus g f prime. You may have also heard it before as u and v. So like u v prime plus v u prime. All of those work. Just it's important to know that when you have you're differentiating a function where you sort of can't separate out f and g. It's really two things multiplied by themselves. You need to use the product rule and separate them out into these two terms. F g prime plus g f prime. Maybe it's worth, so right now I'm thinking, let me just get through all of the rules of differentiation and then we'll look at some examples. If that's bothering someone, let me know. Like say, wait, I want to do examples first before we go on. But I think this is it. These are the only rules I have. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. I only have these 8 rules of differentiation that I want you to know. So let me. My suggestion is let me get through all 8, and then I'll ask. You know, I take it back. You can ask questions at any time. But I'll do some examples after I'm done with these 8 rules. Okay. The quotient rule is just like the product rule, except instead of f multiplying together with g, it's f divided by g. And you know what I tell my students every time I teach this is that I myself do not have the quotient rule memorized. A lot of this stuff I do have memorized. I have everything else, you know, like the quadratic formula, I'll have all this stuff memorized, but the quotient rule I don't memorize, and it's because I can figure it out every time I need to use it, because it's really the same as the product rule. How is it the same? Well, f divided by g is really the same as f times 1 over g. F times 1 over g. That's the same thing as the product rule, except instead of g here, it's 1 over g. And I know how to take the derivative of 1 over g. If anything else, you just use the power rule where n equals -1. So, okay. But if you're the kind of person who doesn't want to do what I do, which is just to figure it out every time I need to use it, then here's a formula that you can use. The derivative of the function f divided by the function g is equal to what I have written here, which is g, just the same regular g, times the derivative of f minus f times the derivative of g. That whole thing over g squared, the function g squared. G of x quantity squared, not the function g x squared. That wouldn't make sense. It's gx all squared. So some people memorize this in various ways with like, they call fu and they call gv. So they would say vu prime minus u v prime over v squared. If you can memorize something like that and it's useful, go ahead. You know, for this class, all of my quizzes and exams are going to be open book and open note. So I don't recommend spending a lot of time trying to memorize things. What I do recommend is doing some practice with derivatives. Just make sure it's one of these learning by doing things. The more you do it, the more you'll notice, oops, I used the wrong rule here. I should have used the product rule, but instead I just added them together, multiplied them together naively, and that's the best way to figure out what's going wrong and what you need to do to fix it. Okay, the last rule is called the chain rule, and it's actually one of the most important ones. And that's because the chain rule is something you will do. You may have learned this already as substitution. Sometimes you'll have a function which there isn't any one rule to show you how to take the derivative of it, but it's sort of like function inside of another function inside of another function. And if you use substitution, you'll be able to solve it. And so the chain rule as I've written it, is it basically as if it's preparing you to do some sort of substitution, where really the thing I care about is y as a function of x. But u is like this sort of intermediary that I use to substitute. Like, let's say you have y equals e to the x plus 1 power. E to the x plus 1 power. I could use the chain rule there by just saying, okay, let u equal to x plus 1. Then I have y is a function of u, which is y equals e to the u. And u is a function of x, which is u equals x plus 1. And then I can use the chain rule to solve, which is the thing I care about, dy dx, is equal to dy du times du dx. So chain rule is something you might actually forget about. You may think you're done with some function, and then you'll remember, oh wait, there's still this chain rule I have to work on, because implicitly I made this substitution where instead of x, I thought of it as 3x. Instead of x, I was thinking of it as 3x. Therefore, right at the end, I have to multiply the whole term by 3, because du dx is 3 if u is 3x. We really need some examples to do this, right? Me talking about the rules of differentiation isn't going to remind you of everything that there is to know about differentiation and say, okay, now you're good, you're ready to go. I actually think you do need some examples, so let's do it. And I got these from the Sid Sayer textbook, okay? Remember, there's 2 textbooks for this class. Sid Sayer, I think, is the undergraduate level, and the Chang Wainwright is more of a both undergrad and master's type level. So these questions are from the Sid Sayer, section 6.7. Let's do these. You guys wanna do these and tell me what you get, and then I will help you with any problems that you might have. Sorry, I'm still eating my lunch. How are you guys doing? You trying these problems? I'm trying to look at your faces to see if you're doing it.
Yeah, I'm trying.
Okay. I'll do them on my piece of paper in a few minutes. Just in case you're looking at this and don't know what to do, let me just give you some hints. First one looks like the power rule. You're going to use the power rule. Second one, you're probably going to, if you're smart, you maybe combine this and this. The first and the last term might be combined. And then actually you could distribute it, or you could use the product rule. You have the choice of what to do there. I think for this one, you're going to probably use the quotient rule. If you're smart, it'll be the easiest way. Excuse me. And now for these bottom ones, 6a and 6d, it's asking you to find the intervals where they're increasing. So it's not just find the derivative, but then you have to think about, what does it mean for the function to be increasing? It means that the derivative is positive. So those last two are really asking, not just find the derivative, but find out when the derivative is positive. But I want to make sure, I think right now the focus should just be on being able to take these derivatives. You guys want more time? Or should I start doing these? I'm going to
More
start writing
time.
them out. I won't give the answers yet, but I'm going to start writing them out. 3a 1 over x to the 6. F. I don't know why I picked these because I thought it's a good mixture of problems. One of these was real hard, I remember. I think 6D takes a long time. Wasn't happy with 6D. Shouldn't have left it on. Does anybody want more time before I do these? It's 1:32. Oh no, I have 13 minutes. Gosh, I hope there's enough for you to solve all this. Let's see. I'm gonna I'm also gonna look at the homework and maybe make sure I can give you some hints for the homework. How about that? I think in 13 minutes I can solve these and give you some hints for the homework, and then I will just make it due Thursday. I think we can do it. Okay. Oh, I want to pinpoint now. I want to pin. What's it called? Spotlight. Okay, guys, ready? I'm gonna do these real quick. Hopefully, you got the same answer. This first one, 3. Oh, I didn't write out the last two. That was dumb. The others, let me write. I'll get it later. So the first one is 1 over x to the 6th. That's the same as x to the negative 6th power. This is part of what I skipped in the logarithm and exponential thing, is just getting you more comfortable with writing these either this way or this way. It's the same thing. 1 over x to the 6th is the same as x to the negative 6th power. Now I can use the product rule, the power rule, to say f prime of x equals negative 6x. Now be careful here, it's negative 6 minus 1. It actually goes to negative 7. Hopefully you didn't write negative 5 there. Hope you didn't get tricked there by writing a negative 5. It's actually negative 7. Okay, how about this? You guys have any questions about that one? You get that? Is that what you got? Negative 6 times x. If you wanted to write that, you could always write it as negative 6 over x to the 7th. That would be right too. Okay, how about this next one? Here's what I recommend. Taking this, the square root of x, and multiplying it by x to the negative 1. This is x to the 1/2 power times x to the negative 1 power. And actually you could get negative 1 plus 1/2 is x to the negative 1/2 times x squared plus 1. You know what? I don't want to use the product rule here. I'm going to keep going. Leave this separate and say, I'm going to distribute this out. X to the negative 1/2 times x squared. That becomes x to the 2 plus negative 1/2 squared, which is x to the 3/2 plus x to the negative 1/2. Maybe it is worth it here, just remind you how exponents work. And you know what? You can go back and look at my slides because I talk about it in those slides. But anytime you see something like, x to the a times x to the b, that is equal to x to the a plus b, right? That's just how exponents work. Or if you see something like this, x to the a to the b power, that's the same as x to the ab. Just if you remember sort of these rules, they're sort of identities that they can help you in this class a lot, okay? And also there's, x to the negative a equals 1 over x to the a. Oh, there's also this one, x to the 1 over a equals the 8th root of x. These are just different ways of writing the same thing. But anyways, I think I used that here to get to this point. I used some of those rules to get here. Now I'm ready to take the derivative of it. F prime of x equals, the derivative of x to the 3 halves is 3, oops, that's a 3, halves x to the 3 halves minus 1 power, that's 1/2, plus negative 1/2. I take that because that's the exponent here, negative 1/2 times x to the negative 3 halves power. I think that's an answer if you can see it. Okay. Maybe I need a sharper pencil. Can everyone see that answer? Did somebody get a different answer by using the product rule? Or maybe actually the same answer by using the product rule. Did somebody do that? Okay, how about this one? You did? You got the same answer using the product rule?
Yeah, I did.
Awesome. Okay, because you could have done that too, like taking this times this or this times this and using the product rule. Let's use the quotient rule here for this 3f. And you know what? I am going to use the mnemonic. I'm going to go back at my rules and say, what was that mnemonic again? It is this. If I take u over v and I want the derivative of that, it is equal to v u prime minus u v prime over v squared. Okay, I got that from the rules. So now let u equal this 3x minus 5, let v equal this 2x plus 8, and we can just use this formula to get the derivative. It should be v is 2x plus 8, I'll just write that, times u prime is 3, times 3, minus u is the numerator, 3x minus 5, times v prime, which is 2, all of that over v squared, which is 2x plus 8 squared. I think this is the answer. It doesn't look very cleaned up, but it is the answer. If you wanted to, you could certainly make the numerator look nicer by multiplying out and combining the like terms. In a homework, I would sort of prefer that. It may be easier to grade if you do that, but generally you don't have to. I can, it's not something I'm going to take off points for because like you didn't do enough simplification for me or something. It's a matter of preference. I would prefer it, but I won't insist. You guys have any questions about this? How would I simplify this? Let me just do it real quick. 6x minus 6x. Wow, the x's go away. I guess so. Minus negative 5 times 2. That's actually plus 10. Looks like this all just becomes 34 on the top. Equals 34 over 2x plus 8 squared. Anybody get something like that when they simplified it? Well, okay. What else should we do? You know what? I'm gonna hold off on the what makes something increasing or decreasing because that's not on your homework. I'm instead gonna focus on what is on your homework, and that's these problems. And I want you to be able to do that. Might even give you some hints right now. Okay, so 4A should be real easy, I think. 4B looks pretty easy. You're going to have to use the quotient rule, but of course now instead of a linear term on the bottom, there's this x squared, so it's maybe a little bit harder to take the derivative of what's on the denominator, but you'll still be able to do it. Okay, for C, you have the first time you have a natural log. What you're going to have to use there is, let me give you an unrelated one where you have a natural log of something like here, if natural log of x cubed minus x. Right? If I wanted to take the derivative of that f, what would I do? If you want to, you can use a substitution. U equals x cubed minus x. And now you can think of the chain rule. If you think of this substitution, u equals x cubed minus x, now you can do the chain rule and say, well, f prime of x. Remember, the natural log is special because the derivative of the natural log is 1 over whatever's inside the natural log. So the derivative of natural log of x cubed minus x, where that's u, is just 1 over u. In fact, maybe I'll write that, 1 over u, because it's natural log of u goes to 1 over u. But don't forget about the chain rule. I also have to multiply it by du dx. Okay, so now let's plug in, knowing what we have for u down here, this is equal to not 1 over u, but 1 over x cubed minus x times du dx, which I have to get from this using the power rule. I would say it's 3x squared minus 1. So that's the answer. Okay, sorry.
I have a question for the homework. So in the homework, it says ln x squared plus 1, and then close parentheses plus 4x. The 4x, you can just take the derivative of separately of the ln, correct?
That's correct.
Okay, great. Thank you.
And of course, you're going to add it.
Yeah.
Right? After the fact, you add it. That's right. That was that first rule that I showed you, or maybe it was the second. But you can always separate things if they're just being added or subtracted.
I have a question.
Yeah.
Could you do another example of the chain rule? Because I remember, but I'd like to see another example if possible.
Okay, I do have very little time. Can I? Do you want to meet me after class or outside of class, and then I'll give you another example?
Yeah, that's fine.
But for right now, let me show you something related to number 4.
Okay.
And that would be the product rule. You got to use the product rule to get number 4. And that is because I'm not going to show you 4, but I'll show you something similar to 4. And that is what? Let me. You want me to do another one for who? I don't know who is just asking me that, but I can do another one that uses the chain rule and the product rule. How about that?
Yeah, it's Kai, but yeah, it works.
Okay, here's one that uses e to the x squared minus 1 times x plus 3. Okay, that's f. I'm going to have to use the product rule here because this times this are two things which I would want to differentiate separately, but they're being multiplied, so I have to use the product rule. And now e to the x squared minus 1 is another chance where I might want to use the chain rule and substitution to say u equals x squared minus 1, wouldn't I? Oops, can you see it? It's off the screen a little bit. Like that. Okay, so what is the chain? What is the product rule? I want to multiply this and this separately. And first I'll take the derivative of this and multiply it by this. So first I want the derivative of, take derivative of this and just the same of that plus the same of this times the derivative of that. That's my method. The derivative of this times the same of this plus the same of this times the derivative of that. And now I'm out of time, but I will if you want, stay with me and I will do this problem. So the derivative of e to the x squared minus 1. I'm going to use this substitution and say e to the u is a function which differentiates to itself. So e to the x squared minus 1 is just like saying, what's the derivative of e to the u? The answer is it's e to the u, except for instead of u, I'm just going to put x squared minus 1. Instead of e to the u, I wrote e to the x squared minus 1 because that's what it is. Okay? But now, because of the chain rule, I have to multiply it by du dx. I have to take this and multiply it by dux. Just doing the derivative of this, I have to include this chain rule part. And that is 2x. Okay? So this whole thing multiplied by 2x. That is just this, the derivative of the first thing. And I multiply that by x plus 3 because that's the same from over there. Here's the plus. Now I have the same thing here, ex squared minus 1. I've just written it down, whatever was there, I wrote the same thing down. I have to multiply that by the derivative of x plus 3, which is just 1. This is the answer. I apologize if I went kind of quickly. I do think, you know, you may have to review this a little bit outside of class, but at least let me get you a definitive answer to this problem. F prime of x equals, I'll write it up a little bit nicer. What if I multiply this 2x times this x plus, yeah, it's not even necessary. I'll just write it as it is. Ex squared minus 1 times 2x times x plus 3 plus e to the x squared minus 1. I'll leave out the minus 1, but that's it. So here's an example where I had to use the product rule, which is this derivative times same plus same times derivative. And I had to use the chain rule in order to differentiate just this part. Just this part here required the chain rule to say, I'm taking the derivative of e to the x squared minus 1. If I treat u as x squared minus 1, then I'm saying e to the u becomes e to the u. This part here is the e to the u. This part here is the du dx. That's how I got the chain rule. So I hope that you will do this for this last problem on your homework. See what's happening here in the homework? You're gonna have to use the product rule where this first term is the u and this whole second term is the v. And you should be able to get an answer for that, for dy dx. Using the rules that you know for differentiation, the 8 rules that I gave you. You guys have any questions about that? Some of you left. Some of you left because the class period has ended, and that's fine. I'll try to post this so you guys can come back and look at it. But, you have any other questions?